mentioned already the NEWAC technology program, where we investigated mechanically actuated asymmetric active clearance control system. Concept here is shown here. Basically, it consists of putting actuators, several actuators of a certain difference for every compressor stage, and you move the segments that shield the casing from the blade, and therefore you set the target clearance at any point of time. In this case here, this has been combined with an active control strategy, and we could show that combining these two strategies, the compressor, so active surge control for the front stages, clearance control for the rear stages, it was possible to enhance the operating range over the full compressor map, so for high speed and for low speed.
How many points do you have to measure with sensors to work into that active control there? Is it multiple stages?
Here we had 4 sensors for active sensors, for one stage, 4 sensors.
And that's at various stages of the compressor.
Yeah. Here in this concept would have more stages. Of course, they can be linked to each other, these stages, because they are mechanically linked because of the same casing, the same motor. So it can reduce the number of sensors. But yeah. In this case, you have to have at least 4 active sensors, and you have got some replacements or safeties to have redundancy. Okay, some words about vibration control. Vibrations can be a very bad thing in an engine because they also limit the operating range, especially for the compressor. So you avoid these regions, or you have got schedules where you pass these regions very quickly. And what could be done by active technology is to damp away any vibrations, for example on the airfoil. And here's an example with a small MEMS system, light on the vane, blade, where you damp away these vibrations. That's done with a piezo device. There's also aerodynamic actuation, like pulse jets, which could damp flow-induced vibrations.
Question. Apart from the economics, can piezo devices actually produce enough force to actively damp these large loads?
Yes. Yes, they can.
The force is large, but the displacement is very small.
That's
dependent on the mode. You can't damp away every mode.
The point is that you don't need much force, you don't need much replacement if you're on the right position. So there's one position where any actuation really gives you a large effect. That's an important point in active control. Being in the right position, doing the right thing, having the right frequency, and then you don't need much energy to get a large effect. Okay. Moving on to the combustor. Combustors have instabilities, flow instabilities, which can be very critical because of flame blowout or also any mechanical destruction. There are several actuation techniques which are available to damp any oscillations, flow oscillations, just fuel modulation, acoustic energies, jets, or moving surfaces. The bandwidth of actuation has to be very high here, and also the operating temperature of the compressor is very high, so that's a demanding actuation here. But there are some systems which have been demonstrated, and especially for ground-based gas turbines, there are commercially available systems today. One is shown here. has a sensor, of course, like piezoelectric electric pressure transducer, which measures any pressure fluctuations. They are fed back to a controller and then onto a valve, and this valve modulates the fuel flow. So it gives you the frequency to damp away any vibrations, flow instabilities, and therefore you can operate in a very lean combustion in a very formally unstable region. Especially for ground-based gas turbines, this is a measure which sometimes has been done because problems during operation occurred, and it's a
There's an example where the system has been retrofitted.
yeah, exactly. That's an example where this was really worth doing.
This is in production.
This is commercially available. That's from IFTA. But I think on the website of the RTO there's also a presentation of this system.
How is the lifetime of the DDV valves?
I can't answer that. So, I know they use Monk valves, but I don't know how long they last.
I think they are not operated all the time. It's just under part load conditions where the instability occurred.
Okay. Besides instability control, there's also emission control, which
I think it was a gas turbine with gaseous fuel. Because otherwise you have the problem of all the delays in optimization,
The master schedule.
sprays, and it's easier to control if you have gas as burning medium. Otherwise, perhaps it wouldn't have worked.
Yeah, the actuation for fuel is, liquid fuel is a big issue.
Okay. So let's move on to the turbine then. Shown here in blue, the low pressure turbine, and offscreen the high pressure turbine. These of course have the whole problem of being so hot, so high temperature. So we've got only limited possibilities. But the good message is that we've got very stable flow process here in the turbine, since the pressure gradient is negative, so you move to lower pressure, which gives you a very stable flow, which doesn't give you any major instabilities. But the point is that you can increase efficiency by active control. And increasing efficiency in the turbine is a very good thing, because the effect in SFC, the specific fuel consumption, is very large. So you can really augment your fuel, so bring down your fuel burn. Techniques here are active clearance control, which I already showed. It's the same thing as for compressors. We can have flow control, again with jets, suction, and also plasma actuators, which is an interesting thing. And we've got cooling air control, what Hugo already showed. And I've got the same example, and maybe I can just explain that again in some more detail. This is taken out of the newer program. And you can see the cooling airflow coming from the high pressure compressor. It's extracted here from the main flow. Normally just led onto the turbine to cool here. With this system, you pass through an heat exchanger, therefore cool down the system, the flow. So the cooling airflow has a lower temperature, and you can reduce the amount of fuel you need. Therefore, optimize the cooling of the high pressure turbine as a function of the operating point. You also have got the control system where you can manipulate the amount of cooling air used. You can cool the turbine with an optimized amount, optimized mass flow. At every point you would like to have good efficiency.
With perhaps being switched off during a cruise.
Maybe you switch it during cruise and switch on during takeoff.
Cool blades.
So a good thing would be to have a measurement of the turbine blade temperatures, of course, and then you can have closed loop control. However, that's a challenging thing
Yeah,
to do.
messing with the mind blade temperature is the big thing.
Separation control, as for compressors, is an important thing for tooling machinery, for the airfoils. Here's an example which has been done in a turbine cascade. You can see sensors mounted in the casing and some devices which suck and blow the air. You can see that on the next slide. Here are the positions of the suction and blowing devices. You've got a pump which induces a pressure gradient inside of the airfoil. And then you suck away through it here, where you otherwise would have a separation on the airfoil. So you suck this away, this low movement fluid, and then blow it out here, downstream, and energize the boundary layer here. Therefore, you reattach the flow, which otherwise separates. The separation region causes high losses, and without separation, with just attached flow, you really reduce losses a lot and gain efficiency. So this was active clearance control, flow control as shown here, and cooling air control. And from the sensor part, you always try to measure pressures for flow control, of course, clearances or distances for clearance control. Cooling air control, as I said, would be nice to have temperatures, but this doesn't seem to be feasible at the moment. Nozzle. This nice picture here from the EJ200. So the nozzle has got several functions, and one of the function is that it leads the flow out of the engine to produce a thrust, and by the high velocity you have got, which produces the thrust, we've got shear layers between the low fluid, low moment, low velocity fluid outside of the engine, the aircraft, and the high velocity jet. This causes noise. It's a very important, very dominant source of noise. And what you can do is you can reduce the amount of noise which is produced by this jet by mixing the high velocity flow with a low velocity flow. Therefore you could have special nozzle geometry, you could have also jets. And an interesting thing which has been developed are adaptive chevron nozzles or serrated nozzles.